Okay, welcome back. Today we're going to focus on Chapter 2, Section 5, where we're still going to be doing applications for solving right triangles. In this section we focus on bearing. Now, bearing is a navigational concept. And bearing is something that I learned with this Trig course because I am from the Texas Panhandle where we don't have large bodies of water. But if you have ever gone sailing, maybe learned how to sail, I've had some students who'd been in the Navy who were who had experience with calculating bearing. But it's a great place to see where trig is applied. We've got two different methods that we're going to explore with finding bearing, and you're going to know which one it is based on which information you're given. So for the first method, you're going to be given a single angle such as 164 degrees. You understand that that bearing is a calculation measured clockwise. Now, this is not the direction we're used to seeing for our positive angle measures, but when we're doing bearing problems, we're measuring clockwise from due north. So, for example, if I'm given a bearing of 32 degrees, then I understand that that is 32 degrees rotated clockwise from north. So an arrow due north is my initial side of my angle, and I'm rotating clockwise. That 164 degree angle that we mentioned, clockwise from due north, is going to put my bearing down here, and of course it gives you a couple more examples. So if you're only given that single angle without any direction values around it, you're rotating clockwise from due north. Okay, now when we are doing these bearing application problems, an accurate sketch is vital. You cannot correctly complete the problem without a good sketch. Okay, we've got radar stations A and B. They are on an east-west line 8.6 kilometers apart. So this is a good time to mention the compass rose. Directions. If you ever use a map, read a map, you've got north-south. Everybody's usually good with those. And then we've got west to east. It reads the word we, left to right. So if we are traveling, the radar stations are on an east-west line, then that is a horizontal line. And we'll put our radar stations A and B on that line. 8.6 kilometers apart. Station A detects a plane at point C on a bearing of 53 degrees. Station B simultaneously, so at the same time, detects that same plane on a bearing of 323 degrees. Find the distance from B to C. So this is what we're being asked to solve, but we need to complete our sketch to figure it out. Now, the first piece of information we're given is that Station A detects the plane on a bearing of 53 degrees. Well, that's 53 degrees from north. So due north of A, there's my due north line, 53 degrees, that's almost 60 degrees. So I'm going to say, okay, that's going to be, if I rotate a clockwise angle of 53 degrees, that's going to be about right here, 53 degrees. And I'm just going to let that straight line travel out. Now, Station B detects the same plane at the same time on a bearing of 323 degrees. So let's think about this. From a line due north of B, 323 degrees, if I'm rotating clockwise, that's going to be 180 to the southern direction, and then another 90 puts me at 270. Well, 360 is a full rotation, so not quite a full rotation is going to be that 323 degrees. So I'm going to say that this bearing line goes right about there. That's my 323 degrees off of due north. And they intersect at this point C, and that's the location of the plane. So let's calculate some things that we know. For example, over here, if A and B are on an east-west line, and I measure my bearing from due north, that means this is a right angle. If this bearing angle is 53 degrees, then the angle inside the triangle is going to be 37, because that's a right angle. So note, the 53 degrees is not an angle inside my triangle that I formed. What about over here? Well, if my bearing is 323 degrees to this terminal line of my angle, that means this is what remains of a full rotation. So this is going to be 37 degrees, not inside the triangle. But again, I've got a right angle here because that is north-south, this is east-west. That means inside the triangle I've got 53 degrees here. Well, 37 and 53 are complementary, so that adds up to 90 degrees, which means my angle C is a right angle. Angle C is a right angle, and we can use our right triangle trig. What am I asked to find? I'm asked to find the distance from B to C. So this is my value that I'm asked to find. The distance from B to C. How far away from Ranger Station B is the plane? Radar Station B is the plane. So I'm interested in using information about angle A. I need to find the side opposite A. The side that I've been given is my hypotenuse because it's opposite the right angle. So opposite over hypotenuse, those are my values for sine. Sine of angle A is going to be opposite over hypotenuse. I need to fill in what I know. Well, I know that angle A is 37 degrees. The side opposite is what we're solving for, and my hypotenuse is 8.6 kilometers. Don't forget your units. I want to keep the right number of significant digits. I notice that I've got 2 significant digits here. You know what? We're not going to focus on the angle measures as much as we are our distance. We've got 2 significant digits for our distance for this distance between the 2 radar stations. So when we solve for that distance from B to C, we're going to keep it to 2 significant digits. You should end up having that round to 5.2 kilometers. Don't forget your units. Pay attention to where your rounding should be. Once again, down here, a correctly labeled sketch is crucial when you're solving application problems, particularly the bearing problems, but always take a few seconds to do that good sketch. It's going to save you time and effort in the end. Let's do one more with this first bearing method, and then we'll switch to the other bearing method. This is a very similar problem. We've got some different values, but we still have the 2 radar stations on east-west lines, so you can start your sketch there. I want you to pause the video, complete your sketch, and see what you can do with this problem, and then come back and see how you did. Hopefully you remembered that the angles that you're given, those angles for bearing, were not the angles inside the triangle necessarily. In this case, they are not. But they do allow us, because the east-west and north-south lines are perpendicular to each other, they do allow us to calculate the values of the acute angles inside the triangles. Once again, our angle C is our right angle. We were told this time that the radar stations are 3.7 kilometers apart. And now we're asked for the distance from A to C. So that's my unknown. Now I can use my angle B, or I could use my angle A again. I still know the hypotenuse. If this is the side I'm looking for, that's adjacent to angle A, and so I can use cosine of angle A. If you chose to use angle B, you would be using sine function for angle B instead. Either way, you should end up with the same answer because remember, cofunctions of complementary angles have the same value. Sine and cosine are cofunctions. So that this side comes out to be 3.2 kilometers. I'm sorry, I labeled it B over here and X over here. Let's change that. Okay, excellent. Let's move on to that second method for calculating bearing. You're going to know that you're using the second method because of what you're given. Instead of being given a single angle value, you're going to be given directions. So you've got bearing that starts either north or south, has an acute angle to show how far, and then a direction to let you know if you are rotating east or west from that north-south line. So for example, if I'm given the bearing north 42 degrees east, that means that I start heading north and then I'm rotating back eastward, so that's to my right or clockwise. For a bearing of south 31 degrees east, I'm starting out heading south and then I rotate again toward the east, which this time ends up being counterclockwise, right? An angle of 32 degrees. So south 40 degrees west, from south, I'm rotating back toward the west. You're going to have to keep in mind that compass rose, north-south, west-east, reads we, the word we, going left to right. Alright, so that's our second bearing method. Let's look at this example. A ship leaves port, sails on a bearing of south 34 degrees west for 2.5 hours, then it turns and sails at a new bearing north 56 degrees west for 3 hours, and if the ship's rate of speed is 18 knots, find the distance the ship is from port. And that sounds like one of those math problems we all make fun of, right? But we can do this. Alright, so we are going to start with the ship leaving port. So I don't know exactly where I'm going, so I'm just going to make port point A out here. It's going to sail in a bearing south 34 degrees west. Well, it's going to head south and then I'm going to swing it back toward the west. That's out toward the left. So from port, south 43 degrees west, 34 degrees west. That comes back this way. So there's my 34 degrees. And it sails for 2.5 hours. I can figure out how many miles that is. I'm wanting to find distance. So instead of labeling this as 2.5 hours, I'm going to come over and say, okay, we're going 18 knots, nautical miles per hour for 2.5 hours. That gets me to 45 nautical miles. So this distance is 45. At this point, our ship turns and it sails at a bearing of north 56 degrees west for 3 hours. So now I'm going to go back toward the north, but I'm still going to rotate out to the west. Still that direction, 56 degrees for 3 hours, so it goes that way for a longer period of time. And now my ship is over here, and I want to know how far it is from port. So this distance, it sailed for 3 hours at 18 nautical miles an hour. So it sailed 54 nautical miles. So this measure is 54. Alright, everybody, keeping up with what we know. What we want is this distance. How far is the ship from port? And we want to figure out, is this a right triangle? If it is, where is our right angle? So I'm going to start looking at my angles. Now, the first thing I notice is that I've got two north-south lines here. So these are parallel, which means that when they're cut by this transversal, I have a special angle pair. My alternate interior angles have the same measure. So if this angle is 34 degrees, this angle is 34 degrees. 34 and 56 is 90. That's my right angle right here. That's my right angle. So I'm going to go ahead and label that C, which makes this B. And I'm looking for my hypotenuse, the side opposite C. Now, what do I know? Well, I know that I've got these two sides. I don't know the measure of these two angles. I know that they are not right angles, but I don't know the measures. But since I know that I'm looking for my hypotenuse, and I have the legs of the right triangle, I can just apply my Pythagorean theorem. I don't know angle A or angle B, but I do know this right angle, so I can use my Pythagorean theorem, a squared plus b squared equals c squared, where I'm solving for C, my hypotenuse. Now when I plug this into my calculator, I've got 45 squared plus 54 squared. I need to take the square root of that. So the square root of that answer comes out to be 70.29 nautical miles away. So that distance is about 70.29, but I need to think about significant digits. So when I go up into my problem, I've been given 3.0 hours, 18 knots, 2.5 hours, so we're looking at two significant digits. Well, if I go to 70, that's one significant digit. If I go to a 0.3, that's three significant digits, and I need two significant digits. So this is one of those cases where trying to keep the exact number of significant digits is just awkward. I need to do 70 in a decimal with nothing after it to keep two significant digits for this problem. So that's what we're going to stick with. Okay, let's do another example. Another bearing problem with our second bearing method. Again, I encourage you to pause the video, read through the problem, set up the sketch on your own, and see how you're doing. It's very similar to the one we just did. Before you unpause the video and check your work. So once again, the ship sails out, turns, and then sails further. And then our question is, how far is the ship away from port when it stops? We've got a different rate of speed, 22 knots this time. Once more, we've got our setup with our parallel lines cut by a transversal. Since this angle is 47, that means this angle is 47. And these two angles are complementary, so there's our right angle. which means we are looking for the hypotenuse again, side C. So we will use our Pythagorean theorem. We want two significant digits still. This one's a little easier. We can round it to 120 nautical miles. All right, example 3. The subtense bar method is a method that surveyors use to determine a small distance between 2 points. The subtense bar with a known length is centered, as you can see. Here's the subtense bar centered at point Q, situated perpendicular to the line of sight between the two values that I'm trying to measure. So I'm trying to measure the distance between P and Q. I set up my subtense bar here so that it is perpendicular to that line of sight. Angle theta is measured and the distance between P and Q can be determined. Now notice that angle theta is that entire angle that is formed. So when we focus on a right triangle, we're focusing on half of angle theta, not the whole thing. We want to find the distance when angle theta is 2 degrees, 41 minutes, 38 seconds. And the length of my subtense bar is 3.5 centimeters. Now, look at that. Why would I keep all those trailing zeros? Well, I'm keeping those trailing zeros because I want to keep 5 significant digits in my problem. I have 5 significant digits here, 5 significant digits here. All right, so what things do I know? I know my angle, and I know the length of the subtense bar. So I'm looking for this side D. If it is opposite, I know the side opposite the angle, and I'm looking for the side adjacent, not the hypotenuse, which means I'm interested in my tangent function. So let's set up the problem with our trig, right triangle trig. The tangent, not of theta. Remember that when we form our right triangle, whether we look at that top right triangle or the bottom, they're identical, they're congruent. We're interested in the tangent of half theta, and that's going to be equal to the side opposite, which is half the length of that subtense bar, so half of B, over the side adjacent, which is the distance I'm interested in. So this is the equation that I'm interested in solving, and I'm going to be solving it for D. Let's go ahead and set that up so that it's solved for D by multiplying, then I'm going to divide both sides by that value tangent half theta. So D comes out to be half the length of the subtense bar divided by tangent of half theta. And now we have some values we can plug in. Well, half the length of the subtense bar is half of 3.5. So 3.5 divided by 2. And then I'm going to divide that by the tangent of half theta, which is my 2 degrees, 41 minutes, 38 seconds, divided by 2. Mostly this problem is an exercise in calculator math, right? So the distance, this distance from P to Q, half of 3.5 is 1.75, and then I've just got to figure out, okay, what is tangent of half theta? Let's figure that out now. So we've got 1.75 divided by, and we're going to divide that by tangent, and it opens that up for us. We can plug in our values here. So we've got 2 degrees plus 41 out of 60 minutes that make 1 degree, plus 38 seconds. Now remember, my denominator for seconds needs to be that 3600, not just 60. Oh, and I didn't do half of it. That is just the tangent of theta. Alright guys, I messed that up. I found the tangent of theta, not half theta. So let's fix that. I'm going to have to calculate half theta, and then we can go back and work it out. So 2 degrees plus 41 divided by 60 minutes plus 38 divided by 3600 seconds. That's my value for theta. I need to take half of that, so I'm going to divide it by 2. So my angle that I'm interested in is 1.3469, and then I've got 4 repeating. Now I can keep that here and I can use it in my problem. That second answer function for my calculator, I'm going to plug in the 1.75 divided by tangent, and it opens that up, and this is where I'm going to use my second answer combination that brings in that angle half theta. That's what I'm after. Now, remember we said we're keeping 5 significant digits, so we've got 74 point, and then I need to round that to 427. 427. And this is measured in centimeters. Alright, excellent. Sorry about the flub, but you need to see that everyone has to stop and think and recalculate when we make mistakes. Okay, how much is going to change how much change will there be in the value of d if theta is 1 second larger? So I've got to do 2 things here. I need to figure out, okay, what if theta is 1 second larger? What's my value? And then I've got to figure out how much of a difference that is from the previous length. Well, I've already done most of the work. In fact, I can go right here and I can say, okay, well, the distance between P and Q hasn't the distance between P and Q has changed. The subtense bar has not changed, so that is still 1.75. I'm still using tangent, but what has changed is going to be this value for the half theta. So let's go in and let's say if theta is 1 second larger, then that means that theta is going to be 2 degrees, 41 minutes, 39 seconds. So this shows us the importance of not rounding in the middle of the problem, because if I had rounded, I probably would have already messed up the exactness of this difference, right? Okay, so there is theta that is 1 second larger. I'm going to take half of that because that's what I need, half theta. So I've got 1 point, and this is what I had previously. This is what half theta is now. So you can see that, yep, it's a little bit bigger, but not a lot. I'm going to write it down, but I'm not going to use what I wrote down when I go into work my problem. I'm going to use that second answer function so that I have not rounded my values. Alright, so to find the distance, I take the half the subtense bar, 1.75, divide it by tangent of this new value for half theta, using that second answer combination so that I have not used an approximation. There's my new distance. We will round that off to our 5 significant digits. And then I need to find, that's not my answer, I need to find how much the distance changed. What happened to the distance? Well, notice that this distance is shorter. That means when my angle increased, it increased because these 2 points got closer together. The 2 points got closer together. So when I find the difference between these two, I see that the change was about 0.08 of a centimeter. So always take a second to go back, reread the problem, and make sure that you've actually answered the problem.